Okay, so let's do this problem together. We have a rocket launched from rest. Oh, that's a crazy looking pen. Let's go with blue. From rest. Now when we see from rest, right there we know initial velocity is 0. Steadily increases speed, so it's accelerating, to 27 meters per second. So final velocity equals 27 meters per second. So that's, I believe, this section. We're accelerating, right? We're speeding up. V0 is here, Vf is here, over a 3.9 second interval. So the amount of time is 3.9 seconds. Before exhausting all the fuel. Alright, so all the fuel cuts off at that point. The rocket continues upward, but slows steadily to a stop. Okay, to a stop, that tells me that the second section, I'm going to do it in a different color, that Vf up here is 0, and basically the initial velocity for the red part equals the final velocity for the blue part. So whatever velocity it ended with, right in that middle part, it starts with for our second section here. Oops, let me make that red. Erase that, make you red. So our second section where it's out of fuel, where it's slowing down. And that lasts, to a stop, 1.9 seconds after running out of fuel. So here, t equals 1.9 seconds. All right, now I could call this t2, 1.9 seconds, and v final 2 equals 0 at the top. I could color coordinate. I could just label it on the diagram like I'm doing here, so I kind of put all these knowns in context. That works too, as long as you're documenting the information you have at the time. So we knew the final velocity equals 27 meters per second. We have all of our stuff labeled here. Okay, so that's what we know thus far. We want to know how far did the rocket rise, so that's a displacement. Did the rocket rise while burning fuel? So that means for the initial part, the blue section, how far did it go? So we want to know delta y in this case, because it's vertical. If you did delta d, it's not a big deal, but because it's a displacement. But vertical distance for that portion right there. Now, we could spend the time, we could do this one of two ways. We could first calculate the acceleration and then use a displacement equation, or we could calculate an average speed and then find the displacement from average speed times time. So for this one, I'm going to do an average speed because I have an initial velocity plus a final velocity over 2. Let's see, my initial velocity was 0. My final velocity was 27 meters per second over 2. So my average velocity for the blue section, see, now I wish I would have wrote that at the bottom. It would have been aligned very nicely, but well, next time. Let's see, 26 would be 13, so it's 13.5 meters per second on average for that first blue section. So delta y equals average velocity, 13.5 meters per second, times, how many seconds did that last for? 3.9 seconds. And my delta y is, let's move this over, 13.5 times 3.9, 52.65 meters. That's the displacement for the first part. Alright, so what is the rocket's maximum height? Alright, so that means I need to look at that red section. Alright, the part where it runs out of fuel. So delta y2, second one, right, is I can still do delta v times t, but I'm actually going to calculate the acceleration this time, just so we see two different ways of doing it. Because we also have a displacement equation that goes initial velocity times time plus 1/2 AAT squared. So for funsies, I'll do it the other way, so we kind of get a sense of how to do it both ways. Okay, delta v over delta t. All right, so the acceleration here, my final velocity minus initial. Now my final velocity is 0. My initial velocity was 27 meters per second. That's what it ended that first section with. All right, over how much time? Well, let's see, the time for the second part was 1.9 seconds. So my acceleration is, where's my calculator? All right, so that would be negative 27 over 1.9. It's 0 minus, always final velocity minus initial. 27 divided by 1.9 gives me about 14.21, negative 14.21 meters per second per second. Now, all of that gets plugged into my displacement equation. So, delta y, initial velocity is 27 meters per second. That's going upwards, so it's important that that is positive. I'm actually going to leave the units out only because I'm running out of space here. So, 27, and the amount of time was 1.9 seconds, plus 1/2 times my acceleration of negative 14.21, make some space here, times my time squared, so 1.9 squared. Okay, got some number crunching to do. The physics is done, now we got to do the math. So we got 1.9 squared. 1.9 times 1.9 gives us 3.61 seconds squared. All right, 14.21 times 1/2, 7.105. Don't forget to take care of that negative sign. 7.105. All right. And 27 times 1.9, 51.3. 51.3. So, had it gone at a constant velocity, reloading. Had it gone at a constant velocity, it would have gone 51.3 meters, but it is slowing down, hence the negative sign here, so we're going to decrease that displacement a bit. So if we take 51.3 minus, and I can do this in parentheses here, 7.105 times 3.61. Careful of the order of operations here, but we get 25.65. 5.65 meters. And that's for the second part. But here we've got to be careful, because the question asks, what is the maximum height? Well, I just found the displacement for the red section, for the second part. I have to add that to the displacement I found in the first part, 52.65. So, my grand displacement, 52.65 plus 25.65 equals, oops, that didn't make any sense, 52.65 plus 25.65 equals, not divided by 25.65, 78.3. That means my total height, let's do this in purple because I got a red and a blue, haha. My total height is, what did I just say? I closed it, 70-something.7. You saw it, rewind the video. Okay, so, quick overview. What did we just do? We had two sections that was happening here. We had a section where it was accelerating, increasing speed in the blue. We had a section it was decreasing speed in the red. Ran out of speed at the top. The final velocity for the blue section kind of handed off and became the initial velocity for the second section. We first used the average velocity here to find averaging the initial and final speeds to get an average velocity. And average velocity times time gives us a displacement. So that was a displacement for the blue part. And then we could have done it the same way, but we chose to do things a little differently. We decided to find the acceleration instead. So we found the acceleration, delta v over t. So found the acceleration, plug that into our displacement equation, which can handle absolutely any situation you throw at it. Crunch some numbers, and we got the displacement for the second part, the red part, but the question asked for maximum height. So then we added these two guys together to get like 70-ish something, 77, 78 point something or other. So that is what we did. That was the plan.